guys, welcome to our part 2 of our lesson. So part 1 we were analyzing a simply supported beam with a UDL, and then so we were to get the reactions at point A, C, and then from there we draw bending moments and shear force diagram. So make sure if you want to listen to more of my tutorial and my structures lesson, you can follow me on YouTube Dixon Amagove. That's my channel. So we had gotten reaction A to be 15 and reaction B to be 45 kilonewtons, and then so we used the method of simultaneous substitution. So we got 45, this is 45, and then we got 15 to be. So straight, let's move to part 2, whereby we have to draw SFD and BMD. So for those who don't know, SFD is shear force diagram and BMD is bending moment diagram. Let's go. So so for shear force and bending moment diagram, we analyze per span, because if it's we are assuming if it's a beam, let's say this is a house. Mostly you might find these cases whereby you have a beam running, maybe it can be a continuous beam running from the house straight, and then at the tail end, so you can have such a scenario whereby you have a column, and then this is column 1, column 2, and then you can have maybe mostly a balcony, which is a cantilever. So we can assume that this load case scenario is what we are analyzing here. So you can find that this is a balcony. This might be a room. So it is a common case scenario in building. So you can have a column which is a support, column which is a support, and then a balcony which is a protruding outside as a cantilever. So this is what we are looking at, real case study. So here we have a support A, support C, so which is, we can assume that maybe this is a column, and then a balcony which is a cantilever here. So here we have 4 meters. We have 4 meters, and then we have 2 meters. And then our load was what? Our load was 10 kilonewtons per meter. So per span, this is A, C, and then B. So per span AC, it will be, so let me indicate here, 10 kilonewtons per meter. So span AC, it will be 10 multiplied by 4 to get 40 kilonewton acting downwards. Span CB, it will be 10 multiplied by 2 to get 20. So this is 40 kilonewton. So it's 10 kilonewtons per meter run. So for every 1 meter we have 10 kilonewtons. So for 4 meters will be 10 times 4. 2 meters it will be 10 times 2, 20. So if you add the 2, 40 plus 20, you get this 60 acting at the center. So let's go. Reaction A, reaction C. So our reaction A is 15, reaction C is 45. So here CB, we are going to have 20 kilonewtons because it's 10 kilonewton per meter acting at 2 meters, but it will be acting at the center. So 40 plus 20, 60. 15 plus 45, 60. So summation of vertical is 0. So we have satisfied our first assumption here. Summation of vertical is 0. So let's go. So this is your point 0. So starting here, we have 15 kilonewton positive, because we say that upward is positive, downward is negative. Keep that in mind. So positive 15 up to that point, positive 15. Along the way, it will meet 40 kilonewton. So positive 15 minus downward force negative 15 minus 40. Get my calculator. It will be negative 25. So this is our 0. So negative will be below the 0 line. So we'll have negative 25. So for a uniformly distributed load, the shear force is represented by a straight line. So you join. So this is 15. Join these 2 points. Top up to there. So this will be positive. This will be negative. So negative 25 at point C, we have, this is negative for 25, then we have upward 25. So negative 25 plus 45. What do you get? 20. Get 20. So you'll come upwards up to 20 here. So this 20, this is positive 20, then downward force is negative. So 20 minus 20, it will be 0. So we go back to 0 again. So 0 that way. So that is the shear force diagram. So let's move to bending moment diagram now. Let's move to bending moment diagram. So this is our shear force diagram. So our bending moment diagram is going to be that way. So you're going to have 0. So you're going to start with critical points. So you have point A. So let's name this point point P. So but remember, the theory of structure, where the shear force is 0, or where it crosses the 0 line, is where we're going to have the maximum bending moment. So this is point P. So you have to get this distance here, distance x. You have to get this distance, because this is the point where we're going to have the maximum bending moments. So how do we get point x? So point x, we have a summation of forces at point P is equals to 0. So 15 minus So distance x, we have 10 kilonewton per meter run, so it will be 10 times x. So it will be acting at this, the center of this point here, is equals to 0. So negative 10x is equals to 0. Negative 10x is equals to negative 15. So divide by 10, divide by 10. So x is equals to 1.5 meters. So x is 1. Just there. That's how we have gotten x to be 1.5. So x is 1.5. So we have bending moment at P, and then we have bending moment at C. Those are our two critical points. So bending moment is simply the algebraic sum of moments at one point, considering either side of the beam, either to the left or to the right. So if we consider point P to the left, we are going to have a distance of 1.5. So what we are going to do, point P. So we are going to have 15 by 1.5 minus 10 multiplied by 1.5. It will be acting at the center, multiplied by 1.5. So that will be 22.5 minus 11.25. So at point P it will be 22.5 minus 0.25. So that will be 11.25 kilonewton meter. That is at point P. So we are plotting that at point P, 11.25. So we are going to calculate at point C, bending moment at point C. Point C, it will be point C, instead of getting from, we can consider, because at this side we have a lot of forces, so we can consider the right side. So at point C, we are going to have a force of 20 kilonewton acting at 1 meter, So because our point C is here, this is our point C. So we have a force of 20 acting at distance of 1 meter. So the bending moment there will be 20 multiplied by 1. So our bending moment here is going to be 20 kilonewton. So when we are plotting our bending moment diagram, we are going to move from this point to this point, and then we go back to 0. So we're going to have something like this, to 11.25. Then we move to 0, that one. So the point of contraflecture is the point whereby the bending moment changes sign from negative to 0, where it crosses the 0 line. So this is our point of contraflecture, this one here. You can call it K. So we have to calculate K. So getting K is very easy. You can just say moments at K, considering to the left. So we are going to have 15 multiplied by K, and then subtract 10 multiplied by K multiplied by K over 2 is equals to 0. So 15K minus, so 2125, 5K squared is equals to 0. So this is an algebraic expression. So let's factor in 5K. It will be 3K now let's factor out 5K. Let's not factor out 5K. Let's factor out 15. Or let's divide this by 3 on both sides. So divide by 3, divide by 3, divide by 3. So 15 by 3, 5K. No, let's divide by 5. Sorry, by 5. By 5. So by 5, 15 by divide by 5, it will be, no, by 5 it will be 3K minus K squared is equals to 0. So we can factor out K. So K 3 minus K is equals to 0. So either K is equals to 0 or 3 minus K is equals to 0. So 3 minus K is equals to 0. So K is equals to 3 meters. So K is equals to 3 meters. So guys, that is our analysis for today. So from here you can proceed to design. You can get your critical shear force. So if you look at the shear force diagram, we have 15 kilonewton, we have negative 25, we have 20, then we have 0. So definitely your design shear force is going to be the one with the highest value. So it's going to be negative 25 kilonewtons. And then on the bending moment diagram, we are going to have, we have 11.25, and then we have 20 kilonewton. So 20 kilonewton is going to be your design moment, but I'm not going to proceed further to design. And then on the side of point of contraflecture, so the point whereby the beam is maybe is likely to experience failure, which is 3 meters. the point of contract lecture. You can even check it on Google. It's a point whereby the bending moment changes the sign to become positive, where the bending moment. So I think from here you can make some few observations that where the shear force is 0, we have the maximum bending moment. And then at this point of support is whereby we are getting the design shear force and the design moment. So when we are designing, if it's a cantilever for your project, maybe you have a column here and a column here. So the point whereby you are going to focus more is the point whereby the beam is converting from a simply supported to a cantilever. So this is going to be your area of interest as a design engineer. So, but we can counter check this data so that we can see if we calculate from the left, are we still going to get 20? So let's do that for the last time and then finish up. So point C. So point C. To the left, I'm going to have 15 multiplied by 15 multiplied by 4 minus 40 multiplied by 2. Are you seeing this? At point C, this is our point C, we have 15 multiplied by 4, and then this, the mid span, we have the mid span of 40, so it's exacting at the center. So 40 multiplied by 2. So 15 multiplied by 4 is 60. Subtract 40 times 2, 8. So we are going to have 20 kilonewton. So you still have 20, then you have 20. Or that's still the same 20. You can get it by 20 multiplied by 1, getting 20. So I think this is the way we started on the calculations up to here. So I think very thank you. You can follow me on my YouTube channel, Dixon Amagove YouTube. Also Facebook, Dixon Amagove. So thank you. If you need design work, structural design, my number is 07 103